The main problem that we are trying to solve today is to make precise the notion of continuity. Okay, so that's our goal. That's our goal. Goal is to make this idea precise. And to do that, we will start from absolutely the simplest thing, which is the set. And of course, the set is not very simple. There are several problems come in when you try to define what is a set. So I'll just briefly mention here that we are using the Zermelo-Fraenkel set theory, and there are details related to this particular type of set theory. For example, it makes way for the axiom of choice. So I'm not very much familiar with the gory details of this particular set theory, but for the moment we will assume the intuitive definition of a set, but there are certain details that you might need to check in the long run. So for us, for the moment, a set is just a collection of objects, a well-defined collection of objects maybe, and a collection of objects, and we will right away go into an example of a set, a familiar example of a set, and that is a set of a few natural numbers, let's say 1, 5 and 7, so on. So let's call this A. So these will be the elements of the set, and what we really want to do is define some sort of a map between this particular set and another set, maybe 7 and 8. So there are two sets now, and we want to define a map from the first set to the second set, the first set to the second set, a way to go from the first set to the second set. Now, a set alone is not very interesting. Once you start defining a way of going from one set to another, things become a little bit more interesting. What we really want to do is to define a notion, as I said, of continuity of this map. So let's call this map F, and one example of what this map could be is something like this: 1, 5, 7. Suppose these are the three elements, and we have 7 and 8, and this set is A and this set is B. Make sure that you understand this very carefully, that this particular 7 is different from this 7. This first 7 is a member of the set A. So you can as well write this as 7A, as 5A, like a subscript, just to remind you that this is actually a member of the set A. And similarly, you can use this subscript notation to remind yourself that this is a member of the set B. So this 7 is quite different from this 7. These are two different 7s. They are just symbols for the moment. And we can define a function, we can define many functions between them, a map or a method of going from one set to another. Let's define one such map. Suppose 1A goes to 7B and 5A goes to 8B. Maybe something like this. A simple thing. And 7A needs to go to somewhere, so it goes to 7B, suppose. So this is an example of a map or a function from A to B. So what we do is we write like this. We have an arrow here and we write f. So f is a function from A to B. So we want to understand this function in a little bit more detail. It has, for the moment, this set does not have any more structure. So we want to put some structure on the set, and that structure will be known as a topology. It will be something that will allow us to talk about continuity. Now the question is, what do I precisely mean when I say the word structure? What is the precise meaning of this term in the context of mathematics? So this will be true in other contexts as well, that a structure is usually a choice. A structure is usually a choice that we make. So in this context, what will be the choice? Well, we will first look at the set of all subsets. Of a set. So this is step 1. Look at all subsets of a set and then make a choice of a few subsets. Few of those subsets. Well, you could have chosen all of them. That's also a perfectly good choice. But you could have chosen a few of them as well. So to give an example, we have this set 1, 5, 7, this particular set A. So let's take the set A, 1, 5, 7. Now let's create the collection of all subsets of A. So these are the following. You have the empty set. This is the empty set. And it's a good exercise to show why the empty set is a subset of A. This is a good exercise. Give it a try, okay? To rigorously show. It's a clever argument from using logical connectives, but you can try that. Okay, why the empty set is a subset of A? That's like a homework problem. Okay, now you can take all the singletons 1, 5, 7, and then you have the couples. So 1, 5, 1, 7, and 5, 7, and you have the entirety of the set A, 1, 5, 7. So this is the collection of subsets of A. Very nice. Now you put a structure on this. So what is a structure? You make a choice. Choose some of these subsets. Your action of choosing is equivalent to putting a structure on the set A. That's actually the same thing. So let's make a choice. One such choice could be the following. You could have chosen 1, you could have chosen 1, 5, and maybe you could have chosen 1, 5, 7. This is one such choice. There could be obviously other kinds of choices. Now sometimes this choice that can become very special. So let me write that. Sometimes the choice that you make can become very special. In particular, it can become a world in itself. And I will explain what that means in a moment. But when it becomes very special, when your choice becomes very special, you call it a topology on the set A, set capital A. So this will be one example of a topology. One of your choices, which for some reason has become very special, and I have to explain what are those reasons. But for some reason that particular choice has become very special, that particular choice is known as one example of a topology on the set A. So let's look at what makes a choice. What makes a choice of subsets special? Well, there are really 4 things that you have to check. The first thing is the empty set in your choice of or the chosen collection. So that's the first thing. Is the empty set in your chosen collection. Is the entire set 157 is the entire set in your collection? Whenever 2 sets are there, U and V, whenever 2 distinct sets are there in your collection, then you want the union of them. Union of them should be also in the collection. And there is a little bit complexity in this particular step. I will talk about that in a moment. But for the moment we can think about it like this, that whenever we have 2 members or 2 subsets in your collection, in your choice, in your chosen collection, you can mix them and make another one, and that should also be in your collection. And finally, whenever 2 of them are in your collection, you want their intersection to be in your collection. So intersection should be in the collection. So these are the 4 things you have to check. If your collection of subsets satisfies all these 4 properties, then that collection of subsets will be known as a topology on the set A. Achha, so let's look at an example. So you take the set A 157 and let's make one topology. Let's call it T, which is nothing but a choice of subsets. So let's make a topology. So we will need to satisfy the first 2 conditions. So we will right away put in the empty set and the entire set. Okay, maybe we can put in something more. Let's put the singleton set 1 and let's put the singleton set. Let's put the set 1, 5. Question is this a topology on A? Does it satisfy all the conditions that we want it to satisfy? So try this and tell me this in the private message. If you think that this particular collection of subsets, this choice of subsets is a topology. Give it a try. It needs to satisfy all of these four conditions. That is, the empty set should be in there, the entire set should be in there. Whenever two of them is in there, their union is in there. Whenever any two of them is there, their intersection should be in there. With this particular set of conditions, does this choice qualify for a topology? I mean, you can put the answer in that private message. Will do. Take a little bit of time. Well, we can check that if I take any two of them, 157, we have 1 and we have 1 5. No, I mean, once this choice has been made, no extra element can be added. I'm getting answers. Okay, very nice, Oyon. Yes, it is. This is truly, as some of you have already realized and given an answer, this is truly a topology. Why? Because if the empty set is in there, the entire set is in there. Whenever you see any two of them, you can take their union, and that union is also inside this particular set, collection of subsets. And if you take an intersection, indeed that intersection is also in the collection of subsets. And you can check this with any pair. You can check this with any pair. With any pair. Okay, so now let us introduce a little bit more complexity in this second and the third and the fourth condition. They are a little bit more complicated. Oh, I could have used phi. I just used it to make it simple actually. I could have used phi. That's a good point, yes. Okay, so let's make this second and third statement here a little bit more complicated. What we are saying is, and this is quite important, what we are saying is that this, instead of saying that we can union any two of them, instead of saying that, we can take union of arbitrarily many. So maybe I can write infinitely, where this is interesting, infinitely many members. And if you take the union of infinitely many members, you will get another member. of your collection. How do you know that you will get that? How do you know that you will get that? How do you know that if you take the infinite union of infinitely many members, you will get another member of the same collection? Well, you do not know. If your collection satisfies this condition, only then it becomes a topology. So if you have to choose a collection such that these conditions are satisfied, you have to choose a collection such that these conditions are satisfied. They will not be satisfied by default. Any collection of subsets will not satisfy these conditions. But in this particular case, we do not have infinitely many subsets, so there are no question of this like taking infinite union. But in certain situations, in most situations which we are interested in, this will be necessary. Okay, but you will see the difference in the fourth statement. The fourth statement is finite intersection. So though you demand that infinite union is part of your collection, you will only demand for finite intersections or intersection of finitely many members of your collection to be in your collection. So this is a subtle point, and we will see why this becomes critical in studying some interesting topologies that we will be using in the future. So I'll write these one more time just to clear things up a little bit. You want the empty set or phi or the empty set to be in your collection. So this particular symbol is a member of, is an abbreviation of is a member of. So this phi or the empty set is a member of your collection. The entire set should be in your collection. Well, whenever you can take infinite union, and you can take finite intersection. So when I say you can take infinite union, what does it mean? Well, it precisely means that if you take the union of infinitely many members of your collection, you will get another member of your collection. Again, if you take the intersection of finitely many members of your collection, then you will get another member of your collection. So these are the four conditions. Okay, now that we understand what this particular gadget is, let me remind you one more time that we started up with the set A. This is the set A, and now we will suggestively call it M, because later we want to talk about manifolds. And when we talk about manifolds, at the very basic level, this is just a set. At the very fundamental level, this is just a set. And we will use the first letter of the word manifold to denote the name of that set. Well, intuitively, Bharat, you could mix any number of these sets and stay inside your collection, right? That is a desirable thing, isn't it? I mean, a more desirable thing would be if you take the common part of several of your members. That common part is also in your collection. there is a subtlety when we go to the infinite case, infinite intersection case, as Oyon pointed out. There is a subtlety there. We do not want the intersection of infinitely many members to be inside the collection. The reason is this, Oyon. At the moment, I can say this, that there is a nesting argument. There is a phenomena called nesting. This is the phenomena. There is a phenomena called nesting that can lead to some sort of problems when you take infinite intersections. We will see what that is. We will see what that is as we progress through this class. But it's a good question, Ayan. Why do we discard the why do we not want the infinite intersection or intersection of infinitely many sets to be also in your topology? We will talk about that. It's a good question. Okay, so the reason we want the union and the intersection to be part of this thing, nesting of intervals. Well, nesting of intervals, that is one particular example of the property of nesting, but the general idea of nesting is a little bit more vivid. Okay, so these unions and intersections, why do we want these four conditions? Well, as Bharat, to respond to Bharat's question, it makes a world in itself. It makes a world in itself. You can mix things up and you are still inside the collection. You can take the common things of several of them and you are still in the collection. The entire set is in the collection, the empty one is in the collection. So in some sense, you are getting a world in itself where you can sort of mix and match as much as you can. This is the intuition about why do we want these four conditions. Okay, but again, always remember that you start with a set M. This is the starting point. This is the starting point. And then you choose, let's call it OM. You choose a collection of subsets of M which satisfies the four conditions that we mentioned. Then this particular collection of subsets is known as a topology on M. Usually it is written like M, OM. This is how it's written, the set, and this is the collection of subsets that we have chosen. We could have chosen different collection of subsets and then the topology will be different. Certainly, it's possible to give two different types of topology to the same set. And we will see an example, but even before we see an example, let's look at the standard topology. In the Euclidean space. Okay, the standard topology in the Euclidean space. Now this is we'll see. No, I don't think it can be written like functions. It's for the moment. Just think about it as a collection of subsets of the base set. Okay, all right. So standard topology, so this is an example again that we will talk about. Alright, so we will be particularly interested in RD. So D is a natural number. In fact, for some mysterious reason, I will just, for the moment mysterious, I will use R4. Now, what does this particular symbol mean? What is the meaning of this symbol? Well, it's actually very simple when you are only interested in the set level information. So what is the set level information? Well, it is just a collection of 4 tuples. We call it 4 tuples or 4 tuples. What is the meaning of this word tuples? Well, it is an ordered sequence of elements. Okay, so there are 4 numbers that we will be writing one after another. So maybe 1, 2.3, 4.9, negative 5. This is an example of one element of this set. And we will write all possible elements. We will write all possible elements and call this set M. Okay. So I'll just write it in using usual set notation. Xi is a real number. So R is real numbers. So forget about every other intuition that you might want from this particular set. Erase all the intuition. You do not want to think about or imagine anything at the moment. At the moment, just think about what this set is at its face value. It is just a collection of these 4 tuples of numbers, of real numbers, and each of the tuples are ordered. Ordered means this particular element is different from, let's say, this one. So I use all the 4 same numbers, but I change the order. Well, I made a different element. So this is what we call this collection of elements is our set. So there is no ambiguity in this particular statement. This is very clear. We have M, it's a collection of 4 tuples. Each tuple is an ordered sequence of 4 numbers, 4. Okay. What we would like to do is to put a topology on M. So what does it mean when I say put a topology on M? Well, we know what it is. It is a choice. It is a choice of a collection of subsets of M. So we have to choose certain subsets of M such that those 4 properties are satisfied. Those 4 properties are satisfied. So to do that, we will define a gadget called softball. See, we have not defined the notion of distance in this set. That's a very high level idea. We will not be defining anything called distance. We are just treating them as numbers. Okay. So we will define a gadget called softball. It is a type of subset of M. A very special type, really. Special type of subset of M. And why is it special? What kind of subset is it? Well, it's quite simple actually. We write it like this: B, and then we write a bracket, then we put a little letter P, and then we put a number 5. Colloquially, this number 5 is known as the radius, and this point P is known as the center. But I do not want you to think of this as the center and radius. I do not want you to think of this as a ball either. Do not put in your imagination any shape at the moment. Forget about any shape or anything. Just treat them as a particular set. So what kind of set is this? Well, choose a point P, or choose a P which is again a 4 tuple, xp, x1, x2, x3, x4. This is a fixed, I should write like this, a fixed member that you choose, okay, and then this particular set will have any, or maybe I can just change the letters just to make sure we understand. This is a fixed member, so A, B, C, D, 4 numbers. So this set will contain all the tuples x1, x2, x3, x4 such that this quantity x1 minus a square, yx2 minus b square, plus x3 minus c square, plus x4 minus d square is less than or equal to 25. 25 is the square of this number. You see, we do not need anything fancy. We do not need any notion of distance. x1 is a number, a is a number. You can just take this, subtract them and square them. Similarly, x2 is a number, b is a number. You can subtract them and square them. And then similarly you can do that for all of them and check if that is less than or equal to 25. If that happens, then you put this particular 4 tuple x1, x2, x3, x4, you put this particular 4 tuple in your set. What is the set? This set B that you are constructing. So this is quite simple. You don't have to think of this as anything related to distance, or any roundish figure should not creep into your mind or in your imagination. Let's for the moment forget about all those imagination and treat this in its face value. Okay, so in a moment we will be using the imagination, but for this particular second, think about this just as a set. So what you can do is, this is a subset. This is a subset of M. Why? Because it contains certain elements of M. It contains certain elements of M. It contains certain elements of M. Well, we'll see. We will see on why we don't want that. We want to use as little number of notions as possible at every step to make our constructions as general as possible, and then we can sort of restrict the idea is a little bit more. So anyway, so this is a subset of M, and why? Because it contains some of the elements of M. All right, and what kind of elements? It contains all those four tuples, or all those four tuples that are inside which satisfies this condition, that x1 minus a whole square plus x2 minus b whole square plus x3 minus c whole square plus x4 minus d whole square is less than or equal to 25. Now you could change these numbers. Instead of 5, you can use any positive number, and instead of p, you can use any other point. So all these elements that all these subsets that we have created, we will call them softballs. Call these is a fancy name for these type of subsets. Okay, so that's what we have. We have certain softballs now. These are identified subsets of the set M. Okay, now we will define what is the topology on M. So what is the topology, or rather the standard topology, on M? Okay, so if I have to say what is the standard topology on M, I have to tell you a collection of subsets of M. I have to tell you a collection of subsets of M. So I will tell you a collection of subsets of M which satisfies all those four conditions, and I will do that using the notion of softball. Okay, how? I will do it in a little bit of convoluted manner, in a roundabout manner. I'll say that any element, take any subset, take any subset of M, any subset of M, okay, and then choose a point, a center, or rather choose a point from M, like a member of M. So maybe choose a member of M, one tuple, x1, x2. Okay, let's give a name to this subset. Take any subset A of M. Choose a point from that subset A. So let's say that point is x1, x2, x3, x4. Now I'll give you freedom to choose you have the freedom to choose the radius. So you can make it as small or as large as you wish. So choose that. Choose some radius r. And what is the radius? Well, radius was the second number in this particular thing. Remember? Radius was this particular number in the second slot. Okay, so this square of which will be used here. Okay, so and check if the ball centered at your point of radius r is a subset of A or not? That means, can you fit a softball, maybe small enough, you can make it as small as you want, can you fit a softball entirely inside this subset A, based at every point in your subset A? Now a picture will help. Suppose this is your subset A. Choose any point, let's call it P. Can you fit in a small enough ball about P that is entirely contained in A? And can you do it for every point P? Choose another point P. Maybe you have to change the radius. You are allowed to change the radius. Maybe it's very close like this. Can you do this for every point P inside your A? Can you choose a softball? Can you choose a softball centered at any point in A contained entirely in A? If the answer is yes, then your set A, you take the set A in your topology, in your collection of subsets of M. If the answer is no, then certainly you do not take it. So this is how. So we have M, which is a collection of 4 tuples. Xi is in R, and we have a topology on M where we have several subsets A, B, C, D like this, each of which has this property that if you take any member of this, take any member P of this subset, you can find a radius R, you will be able to find a radius R such that the softball based at P and of radius R is entirely in A. So this is the condition, this is the roundabout way in which we have created these collection of subsets. So this is a very special collection of subset. This is a very special collection of subsets of M. Okay, now you have to check whether or not this collection satisfies all the 4 conditions that we have. And it is a very good exercise to actually write down rigorously without pictures why that is the case. However, the pictures will very easily help you to understand what's going on. So for example, if you have A and if you have B, and if they have an intersection, so A is in that collection, B is in that collection of subsets, and their intersection, you want to show that their intersection is in the collection. That's it. This is, you want this. And it's very easy to see intuitively what's going on. You take a point P in the intersection. There is a ball that fits totally inside A. There is a ball, that's by definition, because A is a member of this particular collection and all the members of this collections have this property. And similarly, there is a ball that fits entirely inside B. Now you can argue that you'll be able to reduce the radius sufficiently to fit a ball totally inside this intersection. Now when you actually try to write this down, you will see that it is not so easy to write it down. It will take a little bit time. So I will strongly suggest that you write this down. Write the proof of why this particular collection of subsets is actually giving us a topology on M. And this is sometimes known as the standard topology. The standard topology. Okay, now why is this a standard topology? Because whenever we use M, if nothing else is mentioned, people use this particular topology. Okay, question. What is the next confusing thing that we will be doing? Well, the confusing thing is the terminology that we will be introducing. This is the most confusing terminology in perhaps mathematics. So we started off with a set. We created a collection of subsets of M. We chose this with all the 4 properties. This is the topology. So members of script OM, members of this thing, are subsets of M, We call these members open sets. We call these members of OM as open sets. Okay, so the first thing to understand here is we could have used the word good sets. I think that would have been much better. In fact, we could have used the word rows sets. You know why? Because whenever we are using the word open, we think of closed sets. Whenever we use the word open, we think about closed. We think that open and closed are opposites of each other. It's not. Similarly, if I use the word good, you would try to imagine something called a bad set. I mean, there is nothing like that. So the most useful thing that we mathematicians could have done is to use a word called rows, like something that doesn't have an opposite, just to prevent any human imagination. So I could have used the word rows sets instead of open sets to denote that it is a member of OM. Now really, that should have been done. Unfortunately, all the books in topology has done otherwise. So we have to stick to this open sets. So let's clear this up for once and for all. What is open set? Let's make this absolutely clear. This is nothing but a member of OM, some chosen topology. On M. So any particular subset of a set cannot by default be open or not open until and unless we choose a topology. That word doesn't make any sense. So just to make good with this idea, let's look at the set A that we started off with. We chose a topology on A, and that topology had these following subsets. Now, once we have chosen this topology, oh, sorry, I chose 7. I could have done better actually. 1, okay. Once we have chosen this topology, this is an open set. This is an open set. This is open set. And this is open set. Why? Because I have chosen this topology such that these are members of my topology. So instead of using this phrase, this set is a member of my chosen topology, instead of using this huge phrase, I say this is an open set. That's all that's happening here. Nothing else and nothing more. Nothing else and nothing more. Yeah, we do not need anything, no notion of limit points, neighborhoods, nothing. Forget about all those things. Forget about everything that you might be thinking. Instead of that, I'll give you an example where this 1, 5 is no more an open set. Just choose a different topology. Let's call it T1. Let's put the empty, we need the empty set. We need the entire set. Let's put 5, 7 in here, just for fun. Nothing else. Now this T1 that we have just created is a perfectly good topology. It has all the required properties. Now when we are using A comma T1, then so in A comma T1, so A is the set, T1 is the topology that we chose. 1 comma 5, this is not an open set. This is not an open set. Why not? Well, it is not a member of this chosen topology. That's it. But in A comma T, if I chose this topology, then it is 1 comma 5 is an open set. So you see the difference, right? The word open set, I'm spending so much time on this because there is so much ambiguity sometimes students face when they hear the word open set, and they are confused at what's going on here. Okay, it's nothing but the fact, and they're thinking, okay, if something is not open, then it has to be closed or something. Nothing like that. Forget about all those things. The phrase open set means it is the member of the topology that you have chosen on this set A. And you could have chosen a different topology and you could have gotten, and that particular subset might not be open anymore. So changing topology could change open sets. Okay, now that we have a set and a topology, we can say what is a topological space. Topological space, forget about whatever you are thinking when you hear the word space, and just take for the face value that the meaning of this particular phrase is a pair. And what is the pair? Well, it is the set and the chosen topology. So once you have the set, once you have the chosen topology, this particular pair, and you may not like this, it might not be intuitive to you, but it is the fact that this particular pair A comma T is what this phrase topological space is. It inherently chooses a topology, and once you have chosen a topology on a set, you get something called an open set. The members of this topology are open sets. Let us quickly define what are closed sets. Closed sets. If A is, okay, maybe I should use M. I should use M, the first letter of the word manifold. So how do we know? So suppose M is my set and T is my chosen topology. If A is an open set means it's a member of the collection of subsets that we have chosen, member of T, then M minus A is a closed set. So it's the complement of A in M is a closed set by definition. Okay, so let's look at an example again, and you should be very clear about this. So suppose 157, this is a set A, M suppose. Let's choose a topology on it. We have empty set, we have 157, we have 1, and let's put in 57 for the heck of it. So this is a perfectly good topology. You can union anything, you will get this. You can intersect anything. If you intersect 1 and 57, you will get 5, the empty set, which is inside here. So it works out. This is a perfectly good topology. Okay. Now let's take an open set 1, singleton set 1. This is an open set. If this is an open set, then M minus 1, so throw out from M1 this is a closed set. Okay, now let me ask you this question. What is M minus 1? If you throw away from M1, what is it that you get? What set do you get? Put the answer in the private message, please. What do you get when you throw away from M1? So remember, M is 157. M is 157. And you are throwing away 1 from M. So what is it that you will get? What set do you get when you throw away 1 from M? Yeah, it's exactly 5, 7. That's what is left out, as many of you are saying this. Very nice. So then 5, 7 is a closed set. Why? It is the complement of 1. But wait, isn't 5, 7 a member of my topology? Isn't 5, 7 a member of my topology? Well, yes. So this is an open set as well. So a 5, 7 has this beautiful property. This set 5, 7 has this beautiful property that it is an open set and a closed set at the same time. This is open and closed at the same time. That's why I say that using the word rose instead of open would have been better. I could have used rose and I could have used jasmine for this other thing, the complement of it. Then you won't think that these are opposite stuff, because at the same time something can be open and closed. Realize why 5, 7 is an open set. 5, 7 is an open set because we chose it to be inside our topology, and that is the meaning of the word open set. It just tells you that this is a member of the chosen topology. But 5, 7 is also a closed set because it is the complement of another open set in M. It is the complement of another open set in M. It is very much possible that one open set is a complement of another open set. If that happens, then it is open and closed at the same time. That's very much possible. Okay, so we understand what is going on here. We understand the notion of open sets and closed sets very clearly, but we really want to do something with this. So before we shut down today, we will talk about the notion of continuity and how can the identity map be continuous and not continuous depending on the topology. Continuous and not continuous depending on the topology. Yes, Bharat. Actually, what Bharat just said is actually correct. What he said is that if I look at this particular topology, this is a very peculiar topology that we just defined. If you take any element of this topology, it is open and closed at the same time. See, if you take 157, this is clearly open because it's a member of this topology. But if you throw away from if you throw away from M the set phi, then you are left out with 157. So this is closed because it's complement of this open set. Again, the same thing is true about the empty set. It's open because it's a member of the topology. It's closed because it's a complement of 157. So it's open and closed at the same time. That can very well be happen. That can very well happen. Okay, that's correct. You're right, Bharat. Okay, now let's look at this notion of continuity. It's a very simple idea. You have two topological spaces. Remember, it's a pair, and pictorially I'm just drawing the set. We take two topological spaces M and N, and I have just drawn the set. And there is a map between M and N. Let's call this map F. Now we have chosen, you cannot talk about continuity before you have chosen a topology. So you have to choose a topology. So suppose we have chosen a topology on this domain. Let's call it OM. And let's choose a topology on the target space. Let's call it ON. Now, what do we want? We want the following thing. We take an open set in the target space. This is step 1. Take an open set in target space. Okay? Look at its pre-image here. Wait, but what is an open set in the target space? What is an open set in the target space? Well, it is a member of ON, the collection of subsets that you have chosen. So this is some member of ON. Some member of ON. You look at its pre-image. Let's call this V. So you want to look at the pre-image with respect to F of this V. Maybe it's something like this. Question is this open? Is this open? What does it mean when I say, is this open? Well, I mean that whatever this subset is it inside this chosen collection of subsets? That's the word open. That's the meaning of the word open. Whatever the pre-image is, now I have to define what is a pre-image. Well, you look at you take the collection of all the points which map into V. So pre-image under F of V is all points in M that maps to V. Remember, you started off with an open set in the target space. It's the starting point. Take an open set in this target space. And you are looking at the pre-image of that open set. And you are asking the question, is it open in M with respect to this topology? If the answer is yes every time, then your map is continuous. If the pre-image of open sets is open, then the map is continuous. So let me write that. If pre-image of open sets is open, then the map is said to be, is defined. This is the meaning of the word continuous. Defined to be continuous. And this can greatly change depending on how you choose the topology. The answer can greatly change. So I'll give you a crude example. And this is a very beautiful example in the sense it uses the identity function. So let's start with a set A, which contains two elements, 1, 2. And then again choose the target space also to be A, 1, 2. So the domain and the target space, both of the sets are the same set. Okay. But we have to choose a topology. Let's choose a topology. So in A, let's choose the topology. This is sometimes known as the coarsest topology. It should contain only the open empty set and the set entire set, because that's what should be there, right? I mean, the empty set and the complete set should be there, and there could be something else as well, but I choose to not take any other subset. So this is really a baby topology, and you can check it actually satisfies all the four properties. Phi is in there, entire set is in there. If you union them, that's in there. If you take their intersection, that's in there. So clearly this is a topology. And for A in the target space, the A in the target space, we choose a different topology. Take the empty set, take the empty set, take the complete set, take 1, singleton 1, take singleton 2. Okay, very nice. Now let's check, let's create a map between these two sets, and it's a very simple map. 1 goes to 1, 2 goes to 2. This is an identity map. This map is F. Is the map F continuous? Is the map F continuous? Well, we have to check. Let's check. Let's look at one open set, this one, in the target space. So that's step 1. Take an open set in target space. So let's take singleton 1, and step 2 is look at its preimage. What is the preimage of the singleton 1, preimage of singleton 1 under this map F? What is the preimage of the singleton 1? What is the preimage of the singleton 1 under the map F? Can anyone tell me? What is the preimage of the singleton set 1 under the map F? It's a very simple answer. It's an identity map. It's just 1, right? Exactly. Very nice. So this is just 1. So is this set 1 open in the base space? Is 1 open in the base space? Well, it's clearly not open because it is not a member of this topology that we chose. It is not a member of this topology that we chose. And therefore, we found that there is an open set in the target space whose preimage in the base space is not open, which basically means this map F, is not continuous. Why? Because we found an open set in the target space whose preimage in the base space is not an open set in the base space. So a simple function as simple as this identity map is not continuous anymore. This is crazy, because in general when people talk about identity maps, they think that it is okay, this is automatically continuous. But it's not, because we sort of played around with the topology. We are getting a hang. So there are several things that we learned today. The first thing we learned is we start with a base set M, then we choose a topology. So this choice of topology, this action of us making a choice, this is called giving a structure to M. We understood that members of OM, which are subsets of M, are called open sets for no good reason. Now, if you delete from M an open set, you will get a closed set if you take the complement of an open set. A set can be open and closed at the same time. And continuity means a map between two topological spaces. Remember, you cannot talk about continuity at the set level. So you need a topology. So a map between topological spaces is continuous if pre-image of open sets is opened. And we know now that depending on the topology, even the identity map may not be continuous. So these are the things that we have learned and we understand today. In the next session, we will be talking about how to use the idea of topological space, how to use the idea of topological space to create some special type of, so our goal will be to create a very special topological space called a topological manifold. And at the very fundamental level, at the very as Oyon is asking, that is this notion of continuity same as the notion of epsilon delta notion of continuity in calculus? It is the same. One can show that this is the same thing, and it's a very good exercise, in fact, to try to show that the definition of continuity. So in calculus, when you are talking about real numbers, you are implicitly assuming that you are having the standard topology on that set. So if you treat the real numbers as a set and then choose the standard topology on the real numbers, and then you have to check that, okay, this definition of continuity that we just mentioned is actually same as the definition of continuity in